So in this video I will show you how to analyze this fitting here, and we will have a part inside of this, a rod really, and this rod will be clamped by this bolt here, which goes all the way through, and there's actually a nut on the other side, so that this whole shape will deform and clamp it, and we will compute this sort of normal or radial force that this creates. So we need to figure out how to model this really, what loads to apply and what boundary conditions to apply, and how to assess that this piece of aluminium is going to deform. So the whole thing is this whole problem is quite nice because it's going to be interesting to model this. There are various ways of looking at this. So that's what we're going to take a look at. Now, I have the 3D model here, and it's pretty much modeled exactly like the aluminium piece is shown. So what is going to happen is that this force is going to be applied on this sort of these two ears, and they will be pressed together by this spring, or this bolt, which can be seen as a spring really. So we could naively say that we are sort of forcing this edge here towards this edge. That could be one way of modeling this, but it would induce a lot of fictive stresses, of course, in this area here, and we need another way of doing this. And there is a feature in SolidWorks to do this. It's called a connector. It's a bolt connector, and it's basically this bolt connector is going to be a stiff spring which forces this area. And since it's not a Dirichlet condition, it's not really we're not forcing these two areas together, then we don't get these high stresses. And if we were to sort of model this as a force acting on this area here, and maybe perhaps another force acting on this other area here, we might do that as well, and but it wouldn't be very physical accurate. It would be more physical accurate than just forcing, than just applying a displacement condition to this. But it's not going to be the same accuracy as using these bolt connectors, which we'll be seeing in a second here. The other thing is we need to sort of understand what we're doing here. So we're forcing this together, all right? That means that this radius will be smaller, and there is a rod in there. So the whole diameter is 30 millimeters, but the rod can be 29.9. It probably is smaller. So if you go here to evaluate, and we can check the measurement of this thing, you see that the radius is 15 millimeters. So the rod is going to be centered, and it's going to be 29.9, and we can actually create a 3D model out of that and have it be in here and have it be rigid. That means it's not a deformable body, and then we just tighten this, and we let it we let it become a contact problem. And then we will see later what this contact pressure is, or the contact stress, or the contact force. Really, we can read that as well. And then we can assume that, all right, we have a sort of friction number that is known and or assumed here, and we can pull this rod using whatever it was here, 500 newtons, and we can see if it actually works or not. So we're going to assume a Coulomb's friction law here. It's just easy to do that and see if this works. Okay, so far so good for the clamping stuff, but how about where's this attached? Well, it's going to be attached to some ground, and if you look at the actual picture here, this thing is pretty massive. So it will stand to reason that this is bolted to the ground. So we can assume that the ground is also going to be much stiffer than the actual body. So we can use either foundation bolts, which is another type of connector, which I will show you in a second, Or we can just lock this complete body up here, this sort of cylindric surface. We can just put a fixture to these, because it's not gonna matter too much. We're not gonna look at the stresses at this area either way. We're mainly interested if this clamping feature stuff here is going to work out or not. The rest of the body is so high dimension that we don't really think that it's going to be an issue everywhere else. As you can see here, this is a potential area wherever you see high curvature, or in fact infinite curvature like we have at this corner here. That is a bad thing. That means, you know, stress constraints. Stress concentrations. So radiuses is a way to go. We have to have internal radiuses basically everywhere, and we will not address this now. We will put radiuses here later, but we'll see what happens. We will get huge stresses here, and in reality, I mean, if you look at this is very rough everywhere, and there are radiuses down there as well, but they are, you know, even if you have a radius that is quite small, it will still need to have a lot of elements there to resolve those stresses, and the stresses will still be high. Even if they won't be diverging, they will be pretty high. So there's going to be some local permanent deformation there, probably, if you just, you know, clamp this all the way. So yeah, this problem is really nice because it sort of tells us how small can this rod be, and this mechanism still functioning. So that's what we're going to do now, and yeah, let's start. So I'm going to create a new study here, and it's going to be a static study. Okay, and if for whatever reason these displacements get too high, SolidWorks will warn me, so I will know that. Now I'm going to apply a material here, and supposed to apply aluminium here, so I'm going to aluminium alloys, and I'm looking for this aluminium here. It's a cast aluminium alloy 356 with the T6 treatment. So basically this alloy will give me a rough estimate on the Young's modulus, and then the T6 treatment is going to bring up the yield stress probably up quite high, so we'll see that. So what was it? 356. I believe it should be in here. There we go. 355. That's not it. Where's 356? Yeah, we'll probably need to create a new material, but I'm not gonna do that. I'm just gonna apply some material here. I don't want to spend too much time on this. So I'm just gonna take some, I don't know, this. Is this higher? Yeah, it's going to be higher. So I don't know. What is this? It's around 70. Everything is around 70. Let's just do some T6 here, and the yield strength is 275. Yeah, I'm gonna go ahead and take this one here. And you can Google the exact material, but I'm gonna go with this. So I'm applying that, and then I'm going to fixate these holes first. So I was thinking just applying these to this, and that's gonna be okay. But how about the actual rod here? We need that as well, because we're going to clamp that, and we don't want to clamp it too much. So I'm going to go back to the model, and I'm going to create a new body here. So I'm going to sketch, and on the surface here I will create a circle that is 29.9. Yeah, 29.9. All right. And I'm going to extrude this 2 directions. right about this. Okay, so I should have two bodies here, and I can go back to the static, and I have two bodies here. Okay, so this one is going to be rigid, so make rigid here, so it's not deformable now. And then I'm going to do a connections advisor here, and I'm going to do a contact set, and I will manually select contact sets. So I'm selecting this, select other, and I have this face. So need to switch to this one, select other, and this face. Okay, now no penetration. That's what we want. We have different types here, but no penetration. And we don't need any friction here. That's we're going to compute that ourselves. And for advanced, we have node to surface. So we could have node to node, node to surface, surface to surface. Node to node is the fastest contact problem solving algorithm. Node to surface is going to be a little bit slower, but we don't need to have a one-to-one mesh in that case, which is quite nice. So we're just going to keep it to that. And surface to surface is going to take the most computational time, but it's also going to be the most accurate. So we're just going to leave it at node to surface here. All right, so now we have our sort of contact problem defined. So this is going to be deformed, but it's going to check if it penetrates this body. And if it does, it's going to calculate how much force is this other body pushing against this body here. That's what we have created in the contact set. All right, now we have additional things here. We could, as I said, we could apply a force to this and another force to this, but in order to make this more physically accurate, I will show you this bolt connector. So it's under the connectors, and we have a bolt here, and I'm just gonna pick the cylindrical surface. So this is for, the first one is for the bolt head. So this is the bolt head here, and then we have the circle edge of the bolt nut, and it's going to be this one, and it's going to automatically compute the head diameter and the nominal shank diameter here, and we'll set this actually to 8 and this to 12 because our holes is a little bit over dimensioned. All right, and then we can select some sort of material here. It's going to use the standard steel material, and that's fine. And then we have the preload here. So we have a certain torque on this, and one of the questions here is, how much torque must be applied on the bolt in order to generate enough force on a cylinder. So that's how we model that with this torque here. So we will start quite low, 2 Newton meters here. So if you have ever messed around with torques and bolts, you will find that 2 Newton meters is quite low. If you have bikes, then if you have some sort of high performance bike, it will usually say what torque needs to be applied on these sort of M4 or M3 bolts, and it's usually in the range of 5 to 6 Newton meters. But since this is a bigger bolt, then we'll start with 2 and then we can go up from there. So that's how we're going to apply our sort of quote unquote force. All right, and this is a torque. We could apply an axial force here as well, but we're going to stick with the fork because that's what the problem was asking. And we also have a friction factor here. We just leave it as it is here. Good. Now that's that. We can also visualize this. I believe it's going to be visualized if we press OK here, and that's exactly what we have. So we have this torque there it is. It's going to be positive in this direction, and yeah, we have a bolt, and that's what is going to force this thing together here. So mathematically, what is happeing here is that basically it's going to calculate what force is going to be applied on that cylindrical or on that edge that we have selected. So there's going to be a positive force in the y direction computed from this bolt here, and it has per meter. So it's going to add, really, well, it's quite interesting. What is going to happen is going to add one element, one dimensional rod element, really. So it's just going to be a spring between these elements here that sort of clamps this together, and that spring will have material parameters, exactly the ones we have selected now, and all of that computation is being handled by SolidWorks for us, so it's quite nice. All right, so now we have the load case, and by load case I mean we have sort of the force, and we have the boundary conditions, and we have this contact problem that is going to happen here. So we will see if this force is enough to really generate any contact. We don't really know. So we will find what force is the reaction force. We will take a look at that, and we will check what the stresses are. So we have two things to consider here: reaction forces, in order to see if this rod actually can be clamped or can be kept in there sturdily by 500 newtons. And the other thing is this going to be okay stress-wise? All right, so now we can create a mesh here, and we will change to a curvature-based mesh to use that algorithm. And yeah, let's just run with this and see what happens. So yeah, so this is quite coarse, and I'm really concerned about this area here. But yeah, let's leave it at that. And we also really would like to have a good enough resolution in this area. So what I'm going to do is I'm going to apply a mesh control on this radius, because this radius is going to be in contact with this first, due to, you know, the geometry of this. So really I'm going to go down to 1 millimeter here and create the mesh from there. And there we go. So I have a mesh control here, and yeah, that's quite okay. And I'm not gonna bother to increase the mesh of this. I'm just gonna keep it as it is, because I don't really care about the accuracy of that contact problem too much. It's the stresses I'm more concerned with than the actual forces here. They can be quite rough. Doesn't really matter to me. Okay. Good. Now what I'm going to do, I'm going to save this document. So I'm going to put it somewhere in a temp folder in the downloads section here. Just doing temp, because it's going to create bunch of result files in there. So yeah, I'm going to copy them over, and I can sort of see that in there I have this result folder. So this is basically just going to probably be my yeah, so that's just a mesh file containing these mesh. That's the only thing we have. So the result files will be generated shortly. All right, so just to make sure that we have everything, we have our solid body here. It's just a it's a stiff body. We have a contact set between these two bodies here, and they can be two parts. I mean, I've just created this within the part, but they could actually be two parts. And we have fixtures on this. For whatever reason, it doesn't really show up. Where are the fixtures defined? Yeah. So, and then we have this contact set with no penetration, and then we have this counter bore with a nut here, and yeah, we're set. So we can we can run this study, and all right, that's a first. All right, so I had a problem with this file. I needed to make a new save, so I saved it as a fitting to, and I've not copied over the result files. And now when I run it, it tells me that I need to, well, fix this body here. So I'm gonna do that because that's what I forgot last time. So fix geometry. I'm fixing this body because otherwise it's just going to run away on me. And yeah, so it is a non-deformable body, and it should work now, otherwise we would have applied material on it. So let's see here what happens. It's solving, can do more here. And yeah, so it's going to do a bunch of iterations now to resolve the contact constraints. So basically it applies the load, it computes the displacements, and it looks at are the displacements penetrating this body, and if they are, it's creating a force that sort of punches back on the surface, and then it tries to find an equilibrium, and that's what is taking this time now. For every element on our mesh here, and on every node, it's going to look at the corresponding elements on this other body and try to figure out where the penetration occurs exactly. And it's an iterative process, so this whole study becomes non-linear. That's why we're waiting. It's not that huge of a model, really. It's a quite small model. We have just 30,000 elements here, and you know, we have 117,000 degrees of freedom, which is not too much, but I mean, just compare this, because this degrees of freedom means that we have a matrix of this size. We have a mass and stiffness matrix of size 117,000 by 117,000. But yeah, time-wise, as you can see, contact problems are taking longer even than non-linear problems, because we don't really know how long this is going to take, since the forces and contact forces need to be resolved to form an equilibrium mechanically. So the thing that happened here was that it aborted automatically because it couldn't find a solution using surface to node contact. So it switched to surface to surface contact, which is slower, but it eventually might generate a actual solution. So we'll see. All right, so we have a solution, and we can check here in the solver messages on the results that it took 6 minutes and 36 seconds. And we have our displacement plot and the stress plots, and for whatever reason the graphics here are all messed up, but we don't really care about that. We care about the these stresses here, and they are exactly where we thought they were going to be. So I'm just going to change the units here. True scale is on, and yeah, let's do nodal values and change this to a discrete model or discrete representation. There we go, and it's much clearer now what happens. We need to resolve this. We need to add radiuses to this because we are getting quite high stress at that region, maybe unnecessarily high, most probably unnecessarily high. Let's change to floating. So we have like 212 megapascals in that region, and let's take a closer look at that. We can do section clipping, and sorry, not section clipping, I meant iso clipping. We can go to iso clipping, and we can see that, where's my slider? There it is. We can see that we have, in that region we have quite high stress. Do we have any high stress anywhere else? Let's just remove these fixtures here, make them hidden, so they don't interfere with our ISO clipping tool. And let's see, yeah, no, the stress is highest in that region. Let me just check that we're not missing anything. Yeah, no, it's highest in that region. We could also turn on in the chart options the maximum annotation, and we can see that indeed it is this region where we have maximum stress, just not to miss this. Okay, so far so good. So yeah, we can play around with the stress later. For now, let's take a look at the resulting forces. So result force, and we want to take not reaction force but contact or friction force, and we're going to select this surface here, which is going to be in contact. Perhaps, yeah, no, it's probably going to be this, and update. And we can see here that we have a resultant force, but we could also choose a coordinate system here, because now we have this XY coordinate system, and we can see that the resulting force is quite high. It's like 83 newtons, but it doesn't really help us too much. So what I'm going to do here now is I'm going to change back to the model, and I'm going to add, maybe I can do it in the static, in this pane as well. I could add, go to feet. First I'm going to create an axis through this here. How about if I do the axis then? Will this be good? No, wrong face. This one. And there we go. Now I changed to a cylindrical coordinate system here. So this is my cylindrical coordinate system, and you can see I have R and Z. So so yeah. So now if I take a look at this this direction here, which is the highest, which is the 107 newtons in the FX, that's exactly what I want. That's my normal force. So it's normal to the surface. So the holding force is 107 newtons. Good. So now I have a way of finding out this the stress, or this normal force. I can write it down, and I can start messing around with my bolt here, apply more torque in order to get to a higher force here, in order to be able to clamp this thing properly, because what we probably have is a friction coefficient of well, let's say 1/3, 0.3 something. So that means that I need to have a higher normal force, maybe perhaps around 1500 newtons, in order to hold against 500 in the axial direction. So that's what we need to do, and that means that we need to increase the torque here. So we need to run this several times. Okay, good enough. Now, in order to speed up these computation, well, first, let's change. Let's add a fillet feature to this surface down here. So here and here, we will add a. Can we get away with 1 millimeter? Full preview. Nah, that's not gonna work. Alright, how about 0.5? There we go, 0.5 works. Let's increase that. 0.78. 0.9. There we go, 0.9. All right, so now we have a nice fillet. If in case this doesn't work, what we could do really is, well, let's see here. We can take, we can do a sketch on this side, and we could just go ahead and do a, we can do a circle around this point here, and just make it, you know, 5 millimeters, and extrude this. So feature, cut, and just, you know, shove this through here, and cut. That's okay. There we go. All right. So this is a trick that is well known in mechanical engineering to alleviate stresses. So now you know too. All right. Go back here and do a additional mesh control. And we want to resolve this stress in this region here, so we might as well go down to 1 millimeter, and just to make sure that this is okay. And let's create a mesh, run this. All right. Now, in order to speed up, I saw that the solver was a FFE plus solver probably, and what we want to do is go to a direct sparse solver, which for this amount of elements and this amount of degrees of freedom is going to be probably faster, especially for contact problems. So let's try that. Remember, we had the last time it took 6.36 minutes, or 6 minutes 36 seconds. So let's see what it takes now. So saving this, and let's run this study. Why sharing violation occurred? Why? What is this? Need to talk to Kalle. I have no idea what this means. All right, so we're up and running now. And it's been 56 seconds here. And we're using the direct sparse solver, which for this amount of elements should be faster. So let's see if it's indeed true. And now we're done. Let's see how long it took. Solver message, 3 minutes. So yeah, it was faster using the direct sparse solver. And we have a solution here. Never mind this weird graphical error here. But what we have is a much lower stress at this section. We can do a ISO clipping to see how the distribution of stress is. And it's quite low. We're down from some 200 something to 186 in the maximum stress, located directly at this region here. And you can play around with this hole here, this hole size. Right now it's 5 millimeters. If you increase it, you will have a much larger distribution of the stresses to take. And you can also play around with the geometry. I use the circular shape because it's very easy to drill. But yeah, you can choose other types of shapes as well. There's probably some optimal shape here. So that's that region. That's the highest stress. If we look at other regions, we see that, okay, we're pretty low here, but also we are using a quite low force. We haven't changed this, so it's still whatever it was. Let's take a look at that. Connectors, counter bore, edit definition, and it's still just 2 Newton meters. So we can increase this to, yeah, we had like 100 newtons. We want much more, so we can increase this to yeah, let's go with 10 and then see where we get, where we're going from there, to see what happens. But yeah, anyhow, this is a way of doing this. Now we could also add bolts to these, but since we're not interested in what happens with the stress here, it doesn't really matter. We can use our fixed boundary conditions here, no problem. And yeah, basically that's how you do this type of analysis.